Hello everyone, my name is Rusul Hashimi and I'll be your moderator and welcome to today's webinar Predictive Data Analysis. I would like to introduce our presenter Dr. Yasser Elshayeb. Dr. Yasser is a professor of engineering at the American University in Cairo. Dr. Yasser is a graduate of Cairo University in 1990 with a degree in mining engineering and had a PhD from Nancy School of Mines in France on the contribution of fuzzy logic to geotechnical risk assessment of some ancient tombs at the Valley of the Kings in Egypt. Dr. Yasser has been active in teaching and research in various engineering subjects rock engineering, rock mechanics, data analysis, culture, heritage management, risk assessment, and project management. Since 2006, Dr. Ashaib was highly involved in setting up of the Euro-Mediterranean policies and dialogues on higher education, research, innovation, and culture. As a focal point of many Euro-Mediterranean programs in Egypt and has also presided many senior official meetings with the Euro-Mediterranean space. Since his early years, Dr. Shaib has developed a passion for various fields of science and knowledge dissemination. So before we get started, I would like to go over a few items so you know how to participate during this session. If you have any questions during this session, please you can type it down in the Q&A down, and Dr. Yasser will answer them at the end of the session. Second, we encourage you all to share the webinar in your social networks and to register with the new courses that are posted in Arab Oil and Gas Academy Facebook page. So, Dr. Yasser, you can start now.
Thank you, Rasul. Thank you very much for this introduction. Good evening, everyone, or good afternoon, or good morning, wherever you are. Today we are going to actually finish the full phase of the course. We will have only one, I think, one lecture remaining, which will be next Saturday. Today we will be speaking about predictive data analysis and predictive data analysis in the sense that since the beginning of this course, we have been looking into data. We have been looking into data different aspects. At the beginning, we started by looking into the visuals of the data, how the data is distributed. I, at some point of time, showed you, for example, the map of the world with the distribution of everyone, where do you come from. We had also some variables, how they look like, how they react with each other. We spoke about correlation, how the variables are correlating with each other. And last time we spoke also about structural data analysis. So we looked into the structure of the data. We looked into how can we map the whole correlation of everything together, how to measure the similarity or dissimilarity of the data with respect to each other. But all of this was not part of a prediction. I mean, it was all about how to look into the data, how to understand the data, how to see it, how does it look like, how does it behave, how does it work together, how does it relate to each other, how is it similar to each other, and so on and so forth. At no point of time we worked on prediction. How can we expect data to look into the future? Maybe the only point of time when we spoke about that when we were speaking about statistical distribution, which may allow us to look into probability of occurrence of an event, or if we have a certain distribution, then we may know that, well, then the next event may, if the distribution of the events of a series of events is following a normal distribution or a log norm or whatever distribution it is, I can predict what will happen in the future or the probability that an event will occur in the future. So that was the only point of time that we did that. But most of the clients, if I can call it this way, that come to ask for data analysis for their data, or that come with their data, or many times when we have our own data, we always ask the question, how can we predict? How can we know that this thing will happen or this thing will not happen? How can we look into the future? Sometimes we call it a forecast, sometimes we call it prediction, but I mean, it's more or less the same meaning, even in language. Today, I'm going to speak about two tools that we use for prediction. One of them is we call it the ANOVA, which is analysis of the variance. So usually we use the term ANOVA in statistics or in data analysis. And I will be speaking also about the linear regression or the regression in general. I mean, regression in general, but I will take the linear regression as an example, as one of the tools of that. And I will show you a lot of I would say examples or disciplines where we have applied those two tools together. Uh, Analysis of the variance. The analysis of the variance, it's a predictive tool that would allow us to use history to predict the future. Usually the problematic that we have, or the problem that we have, is that we have a lot of variables together, and usually, I mean, it works perfectly when you have uh, two groups. Let's say we have collected the data of the 37 people that are attending the webinar now, and in this data we have among them let's say a variable that is called undergraduate and postgraduate. And I would like to make a hypothesis that using I mean, using this data, I can predict if we will be 38 or 39 people attending this webinar. I can predict based on the data whether this newcomer, this new person, or this new two persons that, or this new n persons that are coming into the webinars would be an undergraduate person or a postgraduate person. So I'm putting a hypothesis that actually the data of undergraduate group are different from the data of postgraduate group. This could be true or this could be not true, but I mean, this is usually the prediction that we work with. If you will consider that gender is only male and female, then you can also use that. I mean, you can use also the analysis of variance to predict something new. If you if you look into the behavior of a student in a class, and then you have fail or pass as marks at the end of the year, then you can also use that analysis of variance to do that. If you, for example, if we go to the oil and gas field, if you have the data of wells that have produced oil and others that have not produced oil, you can maybe also put the hypothesis that using the data, I can predict what will be the status of that oil well. Will it produce oil or not produce oil, depending on the underlying data that you have. And usually the data that you have is could be completely, I mean, could be anything. Could be qualitative data, could be quantitative data, could be whatever. I mean, that's not that's not a problem. The way it's used is maybe illustrated in this in this graph, or in those two graphs. In those two graphs, we have here two groups of. I mean, this is a domain that I've worked with before. We were treating here the type of subsidence that happens due to let's say underground works. In this case, it was due to underground mining. This is an area in France where I have worked on this problematic. We had two types of subsidence that's happening that we observe on the ground, and those types were two. I mean, we had brutal, which is like a subsidence that happens all of a sudden, happens very fast, and progressive, which happens quite slowly. I mean, we can observe it happening over a period of, let's say, one day. So in one day, this area will subside of, will have a subsidence of like half a meter or 1 meter. While in the other case, this brutal, it will have, I mean, this subsidence will happen very rapidly. And we wanted to know if we have, I mean, of course, we studied the geology, we studied a lot of data from different subsidences that happened in the past, and we wanted to know for other regions. I mean, we had something like uh, 195 regions that were also undermined, and we wanted to know when the subsidence will happen. Will it happen in a progressive way, or will it happen in a brutal way? And the reason why we wanted to know that is that if the subsidence will happen in a brutal way, in a very rapid way, then we can not evacuate, for example, the population. So we need to take different measures for the population. While if it will subside over a period of 1 day or 2 days, then, well, you can maybe install a monitoring system and then look into what's happening like that. I'm only explaining this in order to give you the feeling of how to use it. If I speak about the oil and gas field, for example, I'll come back to that example. Um, if you have had like 100 oil fields in a specific area, sorry, oil wells in a specific area, and you had a lot of data collected over for every oil well, then you collect, for example, the depth, the sigma, which is the pressure. Maybe you've collected the amount of water that you've injected or that you've collected, the types of succession of layers that you have in the underground, the type of geological structure that you are penetrating inside, and so on. And then you have a variable at the end says that, well, this well number one, we had oil. This well number two, we didn't have oil. This number three, we had oil. Number four, we had oil. Number five, we had oil. But then number 19 or number 20, we didn't have oil. So uh, putting this data together, you can build a model, a statistical model or a data model that will tell you, well, okay, if tomorrow someone will come to you with, I mean, within the same maybe parameter of the area, and will tell you, listen, I have this new area where I have observed that we have this geological structure, this depth, this sigma, this so and so and so, all the data that you've done, that you've collected over the 100 oil wells that you've done before. And I would like to ask, or you would always want to know, if we will really go and dig this oil well, what is the percentage, what is the probability that I will get oil or not? Using data analysis, you can actually do that, which will save you a lot of money, of course, because I mean, digging an oil well will cost a lot of money. So doing it with the data, it's very interesting. And the way we do it is that, like, we use graphs like the one in front of you, and I will show you the statistical or the mathematical reasons behind in the next slide. So you can see, for example, on the left hand side, this graph on the left hand side, if you have measured this variable, let's call it variable X. I mean, I know the name of this variable, but I don't want to disturb you with the name of the variable itself. Let's say that this variable, we'll call it variable X. If I will measure, I mean, I have observed here that usually all the progressive subsidence, when they happen in areas where the variable X value is ranging from, let's say, 0.45 to 0.55 or 0.56. All the brutal ones happen when you have a value of the same variable that is 0.65 and 0.75, for example. So if tomorrow, I mean, if in the future, I will come back to you with an area where the value of this variable X is zero point 0.5, you can certainly predict that. I mean, you can look into this graph and you will say, okay, if it's 0 0.5, then according to the history that I have, according to the model that I've built, most probably the subsidence will be progressive, will not be brutal. On the other hand, if I have measured variable X for a new zone, and I have found that that the value of variable x is 0.7 or 70% or whatever. I mean, whatever the type of the numbers that we use, you can deduct saying that, well, if variable x value is 0.7, then most probably this will be a brutal subsidence. On the other hand, we have other variables, like this variable, let's call it the variable y. And in this variable y, you can predict you can predict something in the future, but you cannot not predict it all. For instance, if I will come and tell you, in the future, I mean, I have a zone that has the variable y with the value of 4, you can deduct yet that, well, most probably this zone will have a brutal subsidence because you have here 0.4, you have here 4, and it's coinciding with a brutal subsidence. But in this case, if I will tell you that the value of the variable y is equal to 8, you will not actually be able to differentiate between the two groups. You can say, well, I mean, if someone will ask me what would I deduct if the value of variable y is 8, I would tell him, I don't know. I mean, you cannot deduct something. And this is what we call in our jargon in data analysis the power of differentiating between groups. So this variable here has a high power of differentiating between the groups. This variable here doesn't have the same power. Actually, it doesn't have a lot of power to differentiate between the groups. To look into this, I mean, to quantify this power of differentiating between the groups, and remember that we always work with multi-variable data. We don't only work with one or two variables. We work with like tens and sometimes hundreds of variables, and of course hundreds or thousands of data points, of rows. Then we need to quantify that power of differentiating. And in order to do that, we use a statistics called sum of squares. And I will explain what sum of squares is. I know that we didn't pay a lot of attention to that when we spoke about it, but I think that maybe I've asked you to look into the literature and remind yourself of some statistics that we had when we were young, when we were at school, actually, not even at the university. And at that time, we studied, or we have still maybe in mind, a statistic called variance, the variance. And what is the variance? The variance is a measure of the dispersion of the data, and the dispersion of the data around the mean. And the way that we mention, or the way that we use, or the way that we that all those who are working in statistics and data analysis describe the mean, or mentions the mean, is by this symbol mu in Latin. So the variance actually is the following: suppose that you have 5 numbers, and you have the average of those 5 numbers, so you have the mean of those 5 numbers. Then in order to calculate the variance, what you do is that you take each number, the first number minus the mean, squared, and then the second number minus the mean, squared, third number minus the mean, squared, fourth number minus the mean, squared, fifth number minus the mean, squared. And then you take the summation of those squares, and you divide them by the number of data variables that you have, which is in this case 5. So this is in general the description of this equation that describes what's the mean. What's the variance? Maybe you know it, and I'm sure that you've studied before. But I mean, we will work with it here. When we speak about the analysis of the variance, we actually call this part of the equation, we call it SS. We call it the sum of squares, because it's it's difference between the value of the data point and the mean, and it's squared, and it is a sum. So it's actually a sum, which is this symbol, sum of some squares. We call it SS, and this is a term that we use in statistics a lot of time. So the variance for me will be SS divided by N, which is the number of the data points. But let's forget about the data points now, the number of data points now, because we have a lot of data points. Statistically speaking, or mathematically speaking, I would say, we've been able to describe or to calculate that the total variance of a whole bunch of data points is equal to the variance inside the groups with an S to the variance between those groups. So I should here, actually I should stop the show here and go here and add an S here. And let me project it once again. Okay, because there was an S that is missing. So the total variance is the variance inside the groups plus the variance between the groups. And in modern terms, as you know, we all work in the era of networking and internet and so on. So we call it the variance intra, which is the variance inside the groups, plus the variance inter, which is between the group. And when you think of those two terms, inter and intra, and when you think about intra-network and internet, or intranet and internet, it's actually the same. It's between networks, that's the internet, it's between networks, and intranet, it's within the net. But anyway, I mean, this is just the modern way of calling things. Usually in statistics, we will use total variance is equal to the variance inside the groups plus the variance between the groups. Now, what we do is that, I think he was a British mathematician around the 19th century. He have invented this statistic, this equation, this number. He said that if we will divide SS between the groups by SS within the groups, we will get a number that is called F. And if this F is growing higher, as long as this F is growing higher, then this variable is able to differentiate between the groups. So the difference between the groups is getting higher. And this is what I called in the last slide, the power of differentiating between the variables. Let me go back to this graph here. So I would expect that the F for this variable X, that we called it X here, is much higher than the F for this variable which we called Y, and when we were speaking about it here in this graph. And this is a way to say that, well, if you want to choose between which one of those two variables to use to differentiate between the two groups in a new analysis, then you should use the variable x, because it has a higher F than the one of variable y. And this is known for everyone in statistics and so on. And of course, we don't usually go and analyze or calculate those by calculator or by hand as maybe I used to do, or maybe some of us has used to do in the past. Everything is calculated automatically, but I just wanted to show you the underlying mathematics, although it's not that complicated, to understand the logic behind. But if you go to R, if you go to any statistical software that you might be using, SPSS, data, whatever, Excel sometimes, and you ask for the F value of a variable with groups, this is what usually will be brought up. So we use this actually to differentiate between those groups, and we use it in order to predict in the future. So if I have the data, if I have the F for every variable that I have in my data, then I can actually use those with higher F to confirm that I can differentiate between the two groups using variable X or variable M or N or whatever. This is a way of prediction, and we use it a lot. Now, I'll move on to linear regression. As I said before, linear regression is a very specific case of regression. And the regression, I mean, the way that, I mean, what we, the reason that we would like to use regression is that we also build on the data, we also build on the history of the data that we have, and then we project into into the future. And here I have a nice graph saying that, okay, well, I have those data points, those circles here, and using those circles, we can build a straight line. You can, I mean, sometimes in statistical software, we call it trend line. But the mathematical, I mean, the statistical or the data analysis name of that line is, we call it the regression line. And we can call it also linear regression line, because it is the line that is mathematically passes by most of the points that we have in this data. And of course, it doesn't pass by everything, because it's a straight line, and you have points here, you have errors. I mean, we call this the amount of errors. So usually the way we do it is to try to position this line within the data in order to make it the most appropriate for this data. I mean, if you look into this graph, if you try to delete this line from this graph, you will find that the points are going like this way. I mean, it's whenever education is increasing, prestige is increasing as well. I don't know how can we quantify prestige with a number from 0 to 100, but I mean, this is just a case that we have. Probably this is a kind of a coding for the prestige, 20% or 40% or 60%, whatever it is. Education could be called number of years that you have spent in education. So 6 years, 8 years, 10 years, 12 years, 14 years, 16 years of education. So, I mean, you have, if you have spent 10 years in education, you have some data points that says, well, your prestige is about 22 or 23. Sometimes in another case, your prestige was about like 28, 29. But also there were data points where your prestige is about 45. So there is like a difference in the prestige for every number of years of education that you've gone through. And the objective was to draw a straight line to show the trend, but also to project into the future. Or sometimes we also use it for interpolation. So suppose that we are looking into this point here on the line, and this point is like 11.5. So if I have 11.5 years of education, what would be my prestige? I mean, based on the data points itself, you cannot do that. And you cannot predict what would be the most possible or probable prestige that you can have. But using data, using this line, you can actually interpolate. You can actually draw. I mean, you can choose which exact point of the line that you want to work with, and have the y for it, which is prestige. The equation for this line is as any other straight line that we have in mathematics. It's y equal a plus bx. That's a very straightforward equation, and so on. But as I said before, there are a lot of errors here. I mean, if you look into this portion of the graph, you have a lot of points that are above actually the line. So if you stand, I mean, let's take this point here. Let's take 10. So 10 years of education, and then you have, if you rely on the line alone, it will give you 40, let's say 42 level of prestige. But if you look into the data points, if you look into 10, you have 20 something, and you have 40 something or 50 something. So there is actually an error. And this is what we call in our jargon as well, the error of estimation. So I'm estimating, I'm predicting that the level of prestige will be 40 something, while in reality, it happened that it was 25, sometime in other cases it was 50 something, and so on. So this is an error of the estimate. And this is actually what pushed a lot of us, a lot of people to think that maybe the relationship between those two lines is not a linear a linear model. It's not a straight line. It should not actually be a straight line. It actually let me take a pen here and say, well, I can say that, I mean, some of us will say, well, maybe it's a function that goes like this. Others will say, maybe it's a function that goes like this. And some other people would say that maybe it's a polynomial, actually, or this one, or that one, or this one. And for every one of those lines or curves that I'm drawing here, you can actually, mathematically, you can have a function. But the methodology is the same. Why do I do this? Why do I say this? I say this because you need to have a model that you would say, well, looking into the data, and this comes with experience, this comes sometimes with facility, that some softwares even will propose to you the best fit. There is something called the best fit. So what we usually do is that we look into the data, and the easiest thing to say is that it's a straight line. Okay, let's do a straight line, and let's know what is the amount of error that we are having. I will not get you into the mathematics, but we just estimate the amount of error that we have. Then you can, I mean, I can come and say, well, it's an exponential function that is going like this, and I will get you the parameters of the exponential function. It's y equal a plus e to the power of x, and let's construct this exponential function, and we put this exponential function inside the data points, and then we calculate the error, the amount of error. If the amount of error is less than the amount of error or a straight line, then an estimation using exponential function is more appropriate, I would say. Well, someone would say, well, it's a parabola or a hyperbola. Why not? Let's try the parabola. Let's construct a parabola. Y equal a plus x squared, or x squared plus something. And let's look into the error as well, the error of estimates. And if the error is less, then maybe the parabola is more plausible or is more doable than the exponential function is more than the linear function that we have here. Some other people would say, well, it's not even a parabola. It's not an y equal x squared. It's y equal x cube, x to the power of 3, which is a function that goes like this. Or maybe some other people would say, it's following a sinusoidal function, which is a cyclic function like this. This is the data that I'm seeing in front of me. Some other people would say, well, maybe it's actually a polynomial function of the power n. So it's y equal x power 5 plus x power 2 plus. You can actually go and try to predict the function that describes the data that you have as much as you like. There is no limit for that. And what's actually judging which function is more appropriate or predicting more or most suitable for my data than another one is actually the amount of error that we have. So I can imagine that if I would put, for this very specific case, if I would put only a straight line, the blue straight line here, I think that if I will have an exponential function, it will be more appropriate than a straight line, and the amount of error would be less than the straight line. But actually the judging, I mean, there are two judging factors here when we think about this regression. The first judging factor is, of course, the amount of error that you have, and the other judging factor is the shape of the function that we will be using. And I will give you a very straightforward example for that. COVID-19. Everyone looked into COVID-19 from a data analysis point of view because something new, we didn't know about it, and we wouldn't know, and we wanted to know when this COVID will end. Will it ever end or not? I mean, we looked into a lot of, we asked a lot of questions. And then came those who are actually studying epidemiology, studying viruses, studying spread of viruses all around the world, everywhere, here and there. And they said, usually the spread of viruses or the epidemic is always is always following this function, which is similar to the normal distribution. So at the beginning you have very low rate of infection, and then it increases with time, and then it accelerates with time, and then it reaches a critical point, and then it starts to decrease, and then the epidemic will end. So the good news is that for every epidemic there is an end. The bad news are that we don't know the parameters. I mean, if you put here days, if you can say that it started in January, in month 1, we don't know when it will end. It will end eventually at some point of time, but when, we don't know. This could be month 12, which is December, next December, and it could be also month 36, which is like December of the year 2022. We don't know. And what we don't know either is this inflection point, when it will start to decrease and when it will start to go accelerating. We can observe things, but we don't know. What actually every epidemiologist and data analyst in the world that has worked on the COVID-19 did was to try to fit the data that we collect from everywhere in the world to this curve that we call it a logistic curve, which is like the S function. So we have you can search on Google the word logistic regression, which is the same tool, but the shape of the function is like an S. So they would fit the data to this logistic regression function, and then you take you continue the curve using similarity, or using like mirroring this function to know when it will disappear. And one other thing that we have discovered is that every country has its own logistic curve, or let's say function, or let's say curve. Every country has its own curve. And this is also very logical. Because the behavior of people in Egypt is different than behavior of people in Italy, is different than the behavior of people in the US, different than the behavior of people in Australia. And we also started looking into similarities of populations. So I did this myself. When I studied COVID-19 propagation in Egypt, I tried to look into countries that are similar to Egypt. And the country that I found that is similar to Egypt behavior-wise, in the propagation of the virus, was Peru. And don't ask me why Peru, because I don't know. It happened like this. The propagation of the virus in Egypt, or the propagation of the virus in Egypt, according to the data that we have collected, is similar to the propagation of the virus that we have in Peru. And I tried myself to fit the model that we have to the for example, to the German model that has preceded Egypt, to the Italian model that has also preceded Egypt, to the Chinese model that has preceded Egypt, but no luck. It didn't work. But I developed some models, and this is why you would hear people in the media saying, well, we have passed the inflection point. We have passed the peak. Everybody spoke about around month May, June, a lot of countries around the world started speaking about the peak. We have passed the peak. Okay, it is dissipating. And the peak was this point. And the bad news is that you only know that you have passed the peak when you have already passed it, because you cannot predict when you will pass it. But the good news are that once you pass the peak, you know that it will be going down, and that's what actually was going in many countries around the world. But we still observe the data of the COVID, and a lot of countries as well starting observing that it did like this. So it dissipated but didn't reach zero, and then it started going up again. And this is the case of, for example, of Spain now. I mean, if you look into the data of Spain, the number of cases that we have in Spain of COVID-19, it went up past the peak and went down, and then recently, I mean, I'm speaking about 2 3 days, the past 2 3 days, the curve is unfortunately going high. Will it go high and go? Let's use colors here. Um, Blue. Will it go high and be like this and go down, because we know that it will go down, or will it go high and be, let me use the green, and it goes like this? This we don't know, but we know that we can fit it to that model. And of course, I mean, learning from the Spanish experience, you can build on an Italian experience, or you can build an Egyptian experience, or you can build a US experience. I mean, we always learn from each other. But we all know, I mean, those who are working in epidemiology will tell you, if you will ask them, they will tell you that it will come down one day. We don't know when, but it will come down. And there is an inflection point. There is an inflection point. There is a peak point. So let's do it this way. And all of what I've been saying for the past, like, I think 10 minutes now, is about regression. So you have data, and you have a model, and you are trying to fit the data to the model. And you continuously do that. I mean, you do this model today, and then you look into the prediction that you have for tomorrow, and then you look into the data of tomorrow, and you compare it to the prediction that you've done yesterday, and you compare these two together. If they are matching, then fine. Then my model and the parameters that I'm estimating for the model are doing fine. If it's not, then you have to change your model, and then you have to rebuild it again and do it again, and then continue the observation day by day. And I mean, I've done this myself for the data of COVID-19, and of course, there's a lot of websites that you can look into those models, and it will show you the propagation and the expansion of the disease, and how it came down. And in some, I don't know if you've seen it before, but the University of Singapore in June actually published a paper on, I think it was 12 or 16 countries around the world, where they have fitted the data to models, and were able to predict, sometimes with some good accuracy, and sometimes with very bad accuracy. They were able to predict the end of the virus in some countries, when it will happen, and so on and so forth. So it is doable, and it is done like that. But you have always two things to take into consideration. First one is the model that you are fitting your data to, or that you are thinking that your data is following. And I'm here putting on the slide the linear model, which is the very simple, the simplest of everything. Every other model is more complex than that. So you need to say that I think that my data is following linear, nonlinear, multilinear, exponential model, whatever, polynomial model, whatever it is following. That's one thing that you need to look at. And the other thing that you need to look at is the amount of error that you have from that model, or this one. I've gathered here a lot of resources, and of course you can have many other resources. I mean, if you type ANOVA on YouTube, if you type linear regression on YouTube, you will find a lot of, or if you type, even if you type regression itself on YouTube or on the internet, you will find a lot of resources, a lot of explanations, a lot of equations, a lot of things that you need to do, and of course, a lot of tools as well. I mean, I didn't go. I mean, I chose not to go to R or to Tableau this time, um, for no particular reason. It's just that I mean, I want you really to explore it yourself, to look into it yourself, and to find maybe some data. I've gathered here some 5 or 6, some 10, maybe 10 videos, but of course, in YouTube you have hundreds of videos that will tell you how to perform an ANOVA in Excel, how to do the linear regression in Excel, how to do it in R, how to do it in SPSS, how to do it in this software, how to and sometimes you have even specific softwares or specific tools that are done in order to look into ANOVA itself or whatever. So by this, I will stop here speaking about the the predictive data analysis, and I will actually show you something that you've asked it for before, which is the analysis of the data analysis that we've done. That I mean, a company that I've worked with, we have done on data coming from the Gulf of Mexico. And let me stop this share and identify. Yes, this is the published paper. So yes, this is it. I'm sharing the screen. This is, well, this is the paper that I spoke about. This is the data that came from Gulf of Mexico, and at that time, 2008. I was working as a shareholder in a company in Egypt called Informatics International, and our main work was actually to work on data mining in the oil and gas field. I mean, that was our the company still exists, by the way, but I hope that I'm not making any publicity for any commercial thing. But anyway, this is a work that we've done on the showing how can we extract information from data in oil fields. And as I spoke maybe at the very first webinar or lecture that we spoke about, the cycle of the data analysis or the cycle of the data mining. Remember that you start by asking a question, exploring the data, collecting the data, preparing the data, looking into the data structure, and then maybe move to prediction of the data, and then you come back and ask other questions and so on and so forth. Yeah, that's the data mining cycle explained here. So you understand what's the business. In this case, it's the oil and gas. You understand what's the data. You prepare the data. You model the data, and then you evaluate, and then you deploy. I mean, in this case, we were speaking also about deployment of this data. And the more you have, the more you can even predict and see into and look into the future. So this is the case study, and you will see here we have, this is the data of injection rates. So we were comparing different fields in terms of injection rates. Well, sorry, different wells. So well 1, well 2, well 3, well 4, 5, 6, and this is the dates and the injections that were done. And of course, we would tie the injection rate to the production rate in order to see what's actually the question that we were asking was, what is the optimum injection rate that we should use for the oil well, and what is also the quality, the parameters of the water that we have to inject in order to obtain the best solution, because we've discovered also that the quality of the water, of the components of the water, the amount of oxygen, chlorine, and so on in the water, it's a factor that plays a lot with the injection, and also with the production of the data. So you have here, yeah, I mean, those were the parameters that we took into consideration, and those were the variables that we had: injection rate, wellhead pressure, reservoir pressure, oil and water, chloride, bicarbonate, sulfate, sodium, calcium, magnesium, of course in water, total iron, on-site pH, dissolved solid salinity. I mean, a lot of variables that we have for the field. And we were able to describe the data. We were able to say, I will show you here, yeah, like the descriptive model that we've seen here. So we had here some variables that were negatively affecting the production rate, some others that were positively affecting the production rate, and we were able to know that looking into the structure of the data. The next, you see here, I mean, the description is, of course, here, the variables that are proportional to the injection rate, or and so on. We mentioned them here. Here, when we wanted to build our predictive model, we didn't actually look into the logistic regression or the linear regression that we've done. We opted for a neural network. A neural network, in the base, in the heart of a neural network, is actually a logistic regression. So, but instead of having a one logistic regression or a one regression model for your data, you actually divide your data into small subsets, and then you can build a model for it. And I'll show you how. I'll show you this concept. Let me come back to the yes, the new share. Let me come back to the presentation, because I can show you. Yes, let's project it. Okay, I want to see this graph. Okay, well, in order to understand how, I mean, the logic behind is that you can actually come to this graph and say, well, you know, this area here, I see a trend that is going this way, a linear trend that is going this way. And this area here, I see a linear trend that is going that way. And this area here, I see another trend that is going that way. Let me try to draw this. Yes. Okay. So here, I'm hypothetically, of course, I have here this one, I have here that one, and I here have that one, and here probably I have that one, and here I have that one. So it's, I mean, actually, what I'm drawing here is not a polynomial function. It's a function that is actually dependent of where you are in the data. So this line here, for me, I mean, supposedly, hypothetically, is the best function that describes the behavior of this data, for example. Now, no mathematics in the world can produce a mathematical function that will fit those lines that I have brought here. And this is where actually neural networks comes into the game, or what I would call, yeah, I mean, like cutting the data into small portions. So you can say, well, if the data values x is between 6 and 8, you can use this function. If the data point is between 8 and 10, you can use this function. If the data point is between 10 and 12, you can use this function. If the data point is between 12 and 14, you can use this function. If the data point is between 14 and 16, you can actually use this function. And actually, if you think about it, this is exactly what neural networks would do. But you don't see it. I mean, you don't see those functions. The neural networks will look into the data, into your data, and will try to understand that uh, which parts of the data are fitted to which model. We don't call it model in this case. We call it some other names, but I will not. I will not get into the details of that one. But usually, what the neural networks would do is that it will collect different small models, smaller models. Will cut the model, the curve into smaller nodes. We call it nodes, and then it will simulate it in such ways. Um, its um, its advantage is that it's very intelligent, it's very advanced, I would say, and its disadvantage is that at the end you don't have an equation. I mean, and sometimes we as humans we like to see equation to look for. So I'll go back to the paper, which is, yes, it's here. So this is what we've done here, that we thought that the number of variables that we have and the complexity of the behavior of the water injection with respect to the production rate is very complex, that we cannot actually use that. So you see here we had some different models. We defined different models, different neural networks, and as I said before, you don't only need the model, you need also the amount of error. And this is what we've had here, what we had here, which is R square. R square is a measurement of the goodness of fit. So the higher the R square, the good is the model. And actually what we have found is that model A, B, C, D, and E are all having like 86%, around 86%. And here comes another skill, I would say. It's optimization. So model A will give you an accuracy of 86% in the prediction, but it uses 12 variables, 12 input. Model B gives you even higher prediction rate, but it uses only 11 variables, not 12. And then you have model E, which gives you 86% as well, and you have only 8 variables. And this also plays a lot for people working in the oil and gas, or in any domain. Shall I invest in measuring 12 variables in order to get 86%, or it's better to use those only 8 variables and get a similar, or sometimes less? I mean, sometimes if I have, suppose if I had here 86% and then I had here like 80% with only 8 variables, I would have, personally, I would have gone for this model and use it better than that one, because it's worth it. I don't need much more variables to measure. So sometimes you weigh your options. How can we do that? Well, there are some conclusions about it, and of course some references you can look at, and you can look into the data and so on and so forth. I've passed this paper to Professor Garhi, and I think that he can also pass it to you. It's public paper in 2008, so it's more than even 12 years now that it has been published. Enjoy it, and definitely you will find a lot of similar papers, maybe better papers that are published on the same subject. If you look into, the literature of oil and gas and data analysis and so on. I think that I have finished for today. I'll go back to to share the presentation again. To say that, as a wrap up, today we've spoken about analysis of variance as a tool for prediction, and we've spoke also about regression as a tool for prediction. And ANOVA is to measure. It's 19 hours. Sorry, ANOVA is to measure the capacity of a variable, a numerical variable, to differentiate between two groups, and it's usually a numerical variable: 1, 2, 3, 1, 1, 5, 0, 1, whatever we code our variable into. It uses the sum of squares, as I explained, and the sum of squares is a derivative of the variance, so it's almost the same thing. And you have here a statistic called f. Whenever the f is increased for a variable, the difference between the groups increases, and this you can find everywhere. Now, linear regression. The reason for using regression, actually, any kind of regression, is that we want to evaluate the trend, or we want to fit the data that we have to a model, whatever the model is. Here I'm just proposing the linear model, but as I said before, there is zillions of other models and inventions, and people would invent different models that fit their data. And we spoke a little bit about logistic regression, which is the case of COVID-19, because we know that this is the model that fits propagation of viruses. And finally, I showed you this paper that has been published in 2008 about the oil and gas field. I have finished, and I hope that you have a lot of questions to ask. And please, 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 again, as I repeat every time that we have a lecture together, go to the internet, look into those notions that I spoke about. I know that I don't say much. I don't go deep into details, because it will take us maybe 50 or more lectures to go into the details of every word that we say. But I trust that as researchers, as you are, as students, as you are, if you are interested in this subject, then you need to read a lot about it. It's not enough to attend a course or two, or a lecture or two, or so on. You need to look into the internet and search for information, and you will get a lot of knowledge. I'm sure that this will be done.
Thank you,
And
Dr. Yasser. Thank
thank you
you.
so much.
We already have a few questions. Omar asked, can two areas have such similarity in structure and parameters, so we can use the data model built for one area and apply it to another area?
Well, this is very tricky. It goes by experience. I mean, what I have experienced myself is that if you look at it from a macro point of view, the model works everywhere. Like I said, in COVID, we knew that the model is looks like a normal distribution function. We knew that, but then if you will have a model from Egypt and you would like to apply it to Italy, this is very risky. Sometimes you need to reprogram your model again and again, because data are different. Those 39 people who are attending this course are representative of the population, of course, but maybe tomorrow, if we will have another 39 people attending another course, their behavior and their data is completely different. So I know that they are following a normal distribution, but this normal distribution for those 38 is maybe different from others.
Okay. Why the terms intra and inter are used for sum of squares? Aren't they used in variance?
Well, we actually in statistics today we use the word variance and sum of squares as synonym to each other, and inter and intra are just names. You can take off inter and intra and think about within groups and between groups. But with the advancement of science and the advancement of technology, people to use the terms of others. So.
Okay. How the term F is growing higher?
If you will compute the term F for the two graphs, yes, maybe this is something that I didn't explain much. If you will calculate F for this graph, for this variable, you will find that its value is much higher than the f for this variable. So that's why I say, if you, I mean, the more f is increased, the more power it has.
Okay. Is there another way to deduce the appropriate function other than multiple iteration?
Uh, no, no,
Oh,
no. I mean, even those softwares that would say best fit, that would calculate for you best fit, what they do is that they just iterate. They just try one model, two model, three model, five model. I mean, I remember in my PhD years, when I wanted to fit some of the data to some of the functions, and I would fill my computer with a list of all imaginable functions that I can think of, and then leave it all night long to do iterations. And then I come back the next day, and it would tell me this function has the best R square or the best fit, and this function has the least, and then I will look into that. Sometimes we rely on experience, as I said before. I mean, we know, or humanity knows that uh, uh, spread of a virus is following a logistic function. So it has to be a logistic function. I mean, it cannot be something different. So this is based on experience. This is not based on anything else.
okay, there is a request from Abdul Bakar. If you can share the data that they will be working on it.
Um, this is actually a coming back question. This is the second time that I asked this question, and unfortunately, I cannot. Data is sometimes, I mean, it's a property of the client sometimes, and sometimes the client doesn't want to share his data with anyone else. My advice is to look into the internet, and again, on the internet you will find a huge amount of databases and data sets that you can use for anything. I mean, if you type data for ANOVA or data for this or data for that, you will find a lot of data.
Okay. Thank you, Dr. Yasser, and that's all for today. Thank you all, and wish you all a lovely evening.
Thank
Bye-bye.
you so much. Thank you so much.